After watching this video lecture, students are going to be able to relate solubility to the polarity of both the solute and solvent. They're going to be able to discuss the effect of temperature and pressure on solubility, and they'll be able to use Henry's law to calculate the solubility of a gas. So we've discussed solutions and the way that they're formed, energetically speaking. So now we're going to look at the factors that affect the solubility, or the ability of a solute to dissolve into a solvent. So first factor is the nature of the solvent and solute. So polarity, charges, things of that sort. The next thing that's going to affect solubility is temperature, and the last thing is pressure. So we've already discussed solvent-solute interactions when we discussed the formation of solutions. And when we talked about that, we looked at the delta H of the mixture representing the solvent and solute intermolecular forces that form during the solution process. Okay, so when two substances have similar intermolecular forces, they're likely to be soluble in one another. The whole like dissolves like. A nonpolar molecule are going to have the correct intermolecular forces to allow them to interact. So with that concept, if we go ahead and we look at a few examples, when we have two nonpolar molecules, in terms of our solute and our solvent, we're going to get mixing. Same thing's going to be true when we have polar molecules coming together. They're going to like each other and be able to mix. And even when we're dealing with ionic compounds, they're going to like to interact with solvents that have partial charges. So something like a polar solvent like water or NH3 are going to allow a solution to be formed because the partial positives and partial negatives on the polar molecule will be attracted to the ions that are present in salt will interact with the partial positives and partial negatives in the polar molecule. So we need to be careful when we're talking about solute-solvent interactions and make sure that we are considering the entire molecule because some molecules have characteristics that are both polar and nonpolar. And so I want you guys to go ahead and look at the examples we have here. We have straight chain alcohols. And what you should notice is that as we go down this chart, the length of the nonpolar alkyl groups grow and get longer and longer, but the number of OH regions on each of these alcohols remains the same. And so what I want you to see here is that most of these alcohols are going to have some solubility in water. Now what you should notice though is that as the chain, the nonpolar region of the molecule gets longer, the solubility in water decreases. Conversely, initially the solubility in a nonpolar solvent is going to be minimal for the methanol example, but as you increase the length of that nonpolar chain, the solubility in the nonpolar solvent increases. So what I want you guys to just kind of take away is that your molecules that are being dissolved don't necessarily only have, this is just nonpolar or this is just polar. Please understand that as molecules get larger and more complicated, they can have, basically a combo. So the nonpolar region, this is the polar region. And basically, as we increase one region or the other, obviously that's going to affect the solubility in a polar or nonpolar solvent. So please make sure that you're considering this when you're looking at the solubilities of various substances. So this practice problem tells us to predict whether each of the following substances is more likely to dissolve in a nonpolar solvent, carbon tetrachloride, or in water, which obviously is a polar solvent. Okay, so if we go ahead and we look at each of these solutes that they've given us, we first need to decide if they are polar or nonpolar. Okay, so here we go. Nonpolar, we know that hydrocarbons are going to typically be very nonpolar. In this situation, we have an ionic compound. All right, we have a positively charged ion, a negatively charged cation. Okay, so that's going to be an ionic compound. HCl is a polar molecule, okay, and I2 is a nonpolar molecule. Okay, so in this context, we can go ahead and apply each of these. Obviously, the polar molecules are going to want to interact with the polar solvent, and the nonpolar molecules are going to want to interact with the nonpolar solvent. So we know that these two are going to be nonpolar, so they're going to want to interact with the carbon tetrachloride, which is a nonpolar solvent. And these two have partial positives or full-on charges that are going to want to interact with the polar molecule H2O. So for most solids, as you increase the temperature, your solubility of your substance is going to also increase. This represents the solubility in grams of the solute per 100 grams of H2O. And what you should notice is that basically all of these salts, solubility is going to increase significantly as you increase the temperature. Now, of course, there's exceptions to anything, but generally speaking, with solids, if you increase the temperature of the solution or of the solvent, you're going to be able to dissolve more of that solid. So gas solubility and temperature is going to be very different from solids. So what ends up happening is that as we increase the temperature, solubility of gases is typically going to decrease. And this is something that we see with, if we open up a soda and leave it on the countertop versus leaving it inside the fridge, the CO2 that's dissolved in that soda solution is going to be less likely to stay in the solution. So that's why you get a flat soda if you leave it out in the warm room versus if you leave it in the cool fridge. So this is also related to thermal pollution. Thermal pollution basically occurs when we dump hot water into, say, a river or a lake, and basically that decreases the amount of O2 that's dissolved in the water, and basically the plants and animals then don't have enough oxygen to live off of, and that basically messes up the entire ecosystem. This is seen really close to like nuclear reactors, where we basically return the water that's been cooled after being heated up in order to power turbines. So pressure is not really going to affect the solubility of liquids or solids. However, it does have a large impact on the solubility of gases. So we have a situation here where we have a gas that's in equilibrium with gas particles that are dissolved in a solution. If we decrease the volume of this container, what we end up doing is we basically increase the pressure of the gas particles that are inside this upper level space. So what ends up happening is by disturbing this system, we disturb the equilibrium. And so in order to reestablish the equilibrium, what's going to end up happening is that the particles that we see here, are going to dissolve more into the solution in order to reestablish the equilibrium that we had before. Okay, so what ends up happening is as we increase the pressure, more of that gas is going to dissolve into the solution, and you're subsequently going to increase the concentration of the solution below. So the pressure associated with the solubility of gases can be looked at with respect to Henry's law, which basically says that the solubility of a gas is going to be proportional to the pressure of the gas over the solution. So kind of what we already just talked about. However, here's a mathematical representation. S sub G represents the concentration in molarity of the dissolved gas. K is a constant, and it's going to depend on the solvent, solute, and temperature. So that's something that I'll typically give you. And Pg is the pressure of the gas over the solution. Okay, so basically what this equation says is that concentration is going to be directly proportional to that pressure. So if concentration of that gas above the solution increases, okay, that usually means that pressure has been increased. Or if I increase the pressure, the concentration of the solution is going to increase. So Henry's law will allow us to figure out things like pressure, or excuse me, things like concentration of the gas in a solution given a specific pressure. So what we're going to be doing here is calculating the solubility, or the concentration rather, of CO2 in a soft drink bottle. Okay, so basically what we're going to do is we're going to use Henry's law. Okay, and we have that situation here. Relates our concentration to our pressure times our constant. Okay, we have been given our constant, so we're going to plug our constant into K. Okay, we're going to plug in our pressure here. We're going to multiply those two together to give us our overall concentration. in moles per liter. So basically this equation can be manipulated in whatever way necessary in order to get either our pressure value or our concentration value.